Okay, so we continue. As already said, today is our 80th lecture in cryptography implemented in Rust. Now we had begun looking at pairing, and today we want to look at pairing groups in details and how to obtain those pairing groups. Let me just remind us what we've done so far and what we mean by pairing groups, so that as we even venture into determining pairing groups, we know what they are. We began with bilinear pairing definition, and we said bilinear pairing was a map mapping elements of group one by group two, this product, elements of this, the product of these elements to another target group. Now, so this group one and group two are additive groups. All of these are elements of the elliptic curve. There are points on the elliptic curve. So there are points on the elliptic curve. Supposing I have the elliptic curve, y is x cubed plus ax plus b. And let me say that this is defined on the field, supposing it's defined on the field FQ. Now groups on this elliptic curve will be additive groups. Now, so I pick one element from the group. Okay, so I come up with a group, the two groups. Of course, there will be various groups on this elliptic curve. There are various groups. Now, suppose I pick one group and pick another group, and from this group I pick an element. Let me say point P, and pick another element, a point here. Let me say Q. So it's members of this. It's members these points that we want to map to another point, and that other point will be a point in this group. To be a point on in this group. Now, this group, members of this group, this is a multiplicative group. This is a multiplicative group. It comes from the same elliptic curve, only that this time, it's the same elliptic curve, only that now we change the field. We use extension of field, and we had looked at this. We extend this field FQ raised to K, where K is the embedding degree. Now, this group, therefore, is from the same elliptic curve defined on this field. And these other two groups are from the same elliptic curve defined on this field. So that's the only difference. Now, these two groups are what we call the pairing groups. These two groups are what we call the pairing groups. And this one is the target group. So today our lesson is on pairing groups, these two groups. How do we determine group one? How do we determine group two? And then in our next lesson, maybe tomorrow now, we'll be looking at getting this. And to do that, we'll be looking at types of pairing. For example, when we talk of Weyl pairing, we'll be looking at Weyl pairing, for instance, tomorrow, and we want to see how now, once we have these target groups, how do we do Weyl pairing to obtain this target group? So that's what we'll be doing. So now we know when we talk of pairing group, what we mean by pairing groups. Of course, we know what, again, we know what embedding degree that I mentioned there is. When we talk of an additive group, I've said the two groups there are additive groups, and this other group is multiplicative. So we know what signs we are using, multiplication, and the other one using addition. Now, pairing groups are very important in cryptography. Of course, we'll be seeing that in terms of when you're doing signatures, when you're doing encryption, and so on, you're using pairing groups. And of course, I said the notion of pairing is still post-quantum, but it depends on how it's approached. It's still, if you do your things using pairing, they would still be secure under post-quantum computers. It would still be secure. Now we have very many things about pairings, and some of them will not be post-quantum secure, but a majority will be post-quantum secure. Now, so I've mentioned the issue of, okay, I've said it's important in cryptography and in zero knowledge and the cryptographic protocols. Then I've mentioned the issue of these two groups, what we call the pairing groups. Now, what is the order of these two groups? Their order is R. Now, I don't know whether you remember this R. Let me remind you what we mean by R. This R, when we did last time, our lesson, we said, for instance, supposing you have an elliptic curve, x cubed plus, let me say x plus 1, just for instance, and supposing that this group has 9 points. Supposing this group has 9 points. Then we looked at the divisors, the prime divisors of this order of the elliptic curve. This elliptic curve has 9 points. That is the order of this elliptic curve. Now, the prime divisors, or the prime factors of 9, the only one is 3. Now, so this 3 is what we call R, is now R. Now, we saw it last time. We were able to come up with groups. We were able to come up with a group of order 3. And we call it R-torsion group. R-torsion group. So that is just again a reminder of what we did last time. So this is supposing it's an R-torsion. Okay, if it's 3, if R is 3, we're expecting that this group will be of order 3. And if R is 5, expecting that this group will be of order 5. And remember that R was just a divisor of the order of the original elliptic curve. So of course, we looked at an example where the elliptic curve had 20 points, and we saw that in that case, R would be 2 or 5. If it has 20 points, the only prime factors that divide 20 are 2 and 5. And from after getting R, we were able to get the embedding degree. It's from there that we got the embedding degree. What was the embedding degree? Again, a reminder. Embedding degree was a smaller k, smaller integer k, such that this will be divided by R. A k that will make whatever is on the right-hand side divisible by R is what we call the embedding degree. The embedding degree, the smallest integer that will make this one divisible by R is what we call the embedding degree. So that was the embedding degree there. And R, that's how we were getting R and the embedding degree. Now, the target group, this one I've said is a multiplicative group. It will still be of the same order, R. And how do you obtain this? We obtain this as a result of pairing. You have the additive group there and this other additive group. Now you go element by element. You take one element, 1 point here, let me say P, another point there, let me say Q, and then you use an algorithm. You'll be looking at those algorithms when you look at Boyle pairing. You use an algorithm, and that algorithm is supposed to give you a target point in this. It might give you maybe R. I give you point R of this group. So that is the introduction on this in today's topic and what we'll be looking at. And then a reminder of bilinearity, what we meant by, see where we talked of pairing, mapping elements of this group by this to the target group. But now this pairing satisfies some properties. We looked at those properties last time. One of the property was bilinearity. And this is that property, that if you have elements, okay, you pick any integers from any integers, and then integer A, add P A times, add Q B times, then E would map the what is here to this, would map it to this. So that is what bilinearity means. Now, what about non-degeneracy? It means that supposing you have two elements that are not identity, then they cannot be mapped to the identity element. So it just ensures that not every element is mapped to the identity. So if you have P and Q, and if both are not identity elements, then you don't expect them to be mapped to the identity element. Those are properties. We looked at those properties. And here I've just mentioned where we can apply the knowledge of a pairing in identity-based encryption, short signatures, and then zero knowledge proofs. Now, a very important thing that we'll be using to find the second group is what we call the Frobenius endomorphism. And this will be assisting us to find this group, and elements of this group. But this one, we will use our last class knowledge from the last class, where we're getting the R torsion groups. But this other one will use the Frobenius endomorphism. So I'll then tell you what it means and how to apply it. Okay, I've defined the Frobenius endomorphism because we require it. Of course, when you're writing your code to give you group G, give you elements of group G2, you would then incorporate in your code the Frobenius endomorphism. And what it says, okay, it's just, this is a map. And this map is mapping this elliptic curve on this field to the same elliptic curve, the same field. And a point will be defined as this. So point xy would be written as x raised to p, y raised to p, where p would just be the characteristic of this field. For instance, when you talk of F5, the characteristic is 5. So P is 5 in this case. And then this map will map the identity element to the identity element. So this is just the definition of the Frobenius endomorphism. And so when you are writing your code, we will then be incorporating this definition so that the elliptic curve remains. The elliptic curve remains on the same field. And then, of course, so we know we'll be doing some extension somewhere, but the field, when you're doing computations on the field, you maintain the computation of the original field. Then a point will be defined like this, and then the identity element will be mapped to the identity element. Just a minute, just give me 1 minute, and then we begin looking at examples. Now, so then we want to look at examples on how to come up with the two groups, the G1 and G2. And then after that, the method, of course, we'll be using to do our manual calculation is the same method we then use to write the code. Because the formulas will be the same. So it's just saying now how do you incorporate these workings in the code. So the first example, I'm given this elliptic curve. Of course, this elliptic curve is just a y square is x cubed. And then the first one is an ax. Then the second one is the b. Because you're supposed to have x cubed plus ax plus b. So the first one, and the field is F5. The field is F5. So our characteristic therefore is 5. So the question is, how do we compute the pairing groups G1 and G2? And after computing them, list the elements of G1 and G2. Of course, it's important to know these elements so that now the pairing itself, you just choose one element from one group and another element from this other group, and you pair them to get the target group, an element in the target group. So that's what we're saying. But today, as we said, we're just looking at how do we get these two groups. I begin with the G1. I want us to find the G1. So to find the G1, we recall what we did in our previous examples. Previously, we discovered that this elliptic curve has 9 points. And of course, we have a code that can be giving us this. We have elliptic code that will give us how the order of the elliptic curve. Then we want to find R, the divisor of 3, the prime divisor of 3. No, the divisor of 9. The prime divisor of 9 is 3. Now, after you have, this is now our R. After finding this R, you now want to find K, the embedding degree. The embedding degree. And of course, this one we said, the embedding degree is the smallest K, which will make this to be divisible by 3. So our Q is 5 in this case. So it's 3 can 3 divide what K will make this to be divided by 3, and you can see that K is 2. So that when you have 25, 5 raised to 2 be 25, minus 1, this will be 24, and you can see 3 can now divide 24. This one you can do by trial and error. And of course, we also came up with a code that can be doing this trial and error for us, but we're not doing it manually, just in case your Q is huge. In this case, our Q is just 5, so you can do it manually. But if your Q is huge, you require a code, and we looked at that code. You can see you're trying this one manually because if K is 1, the result will be 4, and you can see that 3 can never divide 4. And then you try 2. If K is 2, then this will be 24, and you can see that 3 will then divide 24. We are saying that there are so many values that can make 3 divide this, but K is the smallest of them all. K is the smallest of them all. So that is what we pick. Not saying that 2 is the only number that can make 3 to divide this, whatever is on the right side. It's not only 2 that can make it this 3 divisible. But now we pick the smallest of them, the smallest positive integer that will make whatever is on the right side divisible by 3. Now, so since our R is 3, we're supposed to get 3 torsion group. 3 torsion group. And we can also get the full three torsion group. And of course, we looked at this one in our last lesson. When we computed in our last lesson, the full three torsion group, we found it to be this, using our last lesson. This is already computed. So it gave us, how many points are this? This will be 1, 2, 3, 4, 5, 6, 7, 8, 9. This will be 9 points. Okay. Now, but now this is the full three torsion. But what we want is the G1. The G1 is a subgroup of this group. It's a subgroup of this group. It's a subgroup. So elements of this group that when multiplied by 3 gives you the identity. Elements of this three torsion. Three torsion element. So put together the four three torsion. Together, so three torsion group D1. So, instance, when you this means when added to themselves 3 times, when added to an additive group, so of 3p we mean plus give us the identity. Now, so we're talking about how to get G1. And the G1, we had said, first of all, using our previous knowledge, we're supposed to know how to get the full three torsion. The full three torsion group. We know where the 3 is coming from. And then using our previous, of course, we had a code to do this. A code that will be giving us this group. This is the full three torsion group. G1 is supposed to be a subgroup of this. And this subgroup is just a three torsion subgroup. The three torsion subgroup. Now, so what is a three torsion subgroup? This is a group comprising of elements which, when added to themselves 3 times, their result will be the identity. Elements which, when you add P plus P plus P, the result will be identity. So again, we had a code for doing the three torsion. Of course, I have it here. It will give you this element, and this element. So these are the only elements which, when you add themselves 3 times, so 3 times identity, it's supposed to be identity. And then 3 times 2, 1, supposed to be identity. And then 3 times 2, 4, so you're adding it itself, is supposed to be identity. So again, to write this code, you need the formula for adding elements on the elliptic curve, and we know those formulas. We know, of course, how to get gradient, how to get the slope when you're talking of the same point. So P plus P, of course, we are adding a point to itself. So you have a formula for getting gradient in that case. Now, so this gives you 2P. Now 2P plus P is what gives you 3P. And these are two different points. So again, we have a formula for getting gradient when the points are different. So those points, those formulas, you are adding them in the code. You're adding those in the code, and that will assist you to get the summation. So what this code will then be doing to find these points is going through all these points. It's going through all these points, and summing them, summing each one of them 3 times, and seeing which one gives you identity, and then collecting those that gives you identity. And those that gives you identity form G1. They form G1. Once again, you notice that the order of G1 is 3. Order of G1 is 3. Now, what about how do we find G2? And of course, we say that these groups will be of the same order. G1 and G2 will be of the same order. But how do you find G2? I'll show you the code later on, but let's go through the steps again. We now want to determine G2, which is also a subgroup of the full 3 torsion. It's also a subgroup of this group. It's also a subgroup of that group. But now we'll be using the Frobenius endomorphism, as I said. And this will be using, we know that we are dealing with the elliptic curve Q, where Q is the base of this field. It's the base of this. In our case, the base is 5. In our case, I only changed this one to P, but it's supposed to be Q. Our base is 5. So to get G2, knowing that our base is 5, we check each of these points. We check each of the points in the full torsion group. And we want to see which one of them, which one of those two, or which one of those points would satisfy this condition. Which one of them would satisfy this condition? So what does this condition mean? This condition means that if I have point P, and I have some mapping, this mapping maps P. The result that I get after mapping this P should be the same as 5 times P. So I map this point first of all. And this is the mapping of using the definition of the Frobenius endomorphism. This is the definition. That's how we defined it here. That every point shall be written this way. Every point shall be written that way. So after the mapping giving us that, we want to check whether what the mapping has given us equals to 5P, where 5 is the base of the field. Of course, not all these points would meet this condition. But I want to check which ones will meet this condition. So the ones that meet this condition, put together, they give us our group G2. So when you are writing your code, of course, you're putting this condition in your code so that your code is able to get elements that satisfy this condition. And after getting elements that satisfy this condition, putting them together, they give you a group G2. Now, so we of course, your code will be doing it using trial and errors, trying each of these points. It's trying each of these points in the full torsion group, each of these points. Each of them is applying the mapping to each of these points. And then after applying the mapping, compares the result with 5 times that point and see whether the result is the same. So that's what we want to do. We want to try each of these points, not all of them, just a few selected points. And then we see what our G2, of course, we are expecting our G2 to have three points only out of these 9 points, it will have only 3 points. G2 will have only, is a group of only 3 points. So then I've decided to begin with 2, 4. I want to check 2, 4 whether it fulfills the Frobenius endomorphism. I apply the mapping to it. What the mapping says that a pi of 2, 4 should be 2 raised to 5, 4 raised to 5. So I just raise 2 to 5. I get that 2. Just normal raising 2 to 5 is 32. And then 4 to 5 will be 10, 24. And remember, I'm doing this mod 5. I'm doing this mod 5. So reduce this mod 5. This one reduced to mod 5 will be 2. And this one reduced to mod 5 will be 4. In other words, 5 goes into 32. The remainder is 2. And 5 goes into 10, 24. The remainder is 4. So this point is mapped to that. It's only a coincidence that these 2 are equal, 2, 4 and 2, 4. It's only a coincidence, not always the case. It's not always the case, but in this case, it was just a coincidence. Now, we want to check whether 2, 4 added 5 times would give us the same result. Whether 2, 4 added to itself 5 times will give us the same result. If that happens, then 2, 4 becomes a member of the group G2. Okay, I didn't add manually. Of course, I am just showing you that I'm adding this point 5 times. When I did that, I got that it will give me 2, 1. When you add it 5 times, the result is 2, 1. We can add it manually, but of course we have a code for doing this. We have a code for doing this. This is, you begin by adding this. These are the same points on the elliptic curve. These are the same point. So you have a formula for getting the slope. And then after getting the slope, get x3. The way we've been doing, then get y3. The way we've been doing. So you have a new point. Let's call it R. Now this R, add 2, 4 to it. These are 2 different points. So you have a formula for getting the slope again for when points are not the same. When points are not the same, we have a formula for getting the slope. So these formulas, you're giving your code. You're giving your code, and of course you have given it a condition to add a point to itself 5 times. So it knows when to use. When the points are the same, it's using this formula, getting the slope. Then you're giving it a formula for getting x2, x3, then a formula for getting y3. So when it adds p plus p, it knows that this is the same point. So I'm using this formula for getting slope. Then after getting the slope, I get x3 and y3 using this formula, which you're also providing. Then it has r, then adds r to 2, 4. Then it notices that these 2 points are not the same. Then it has, you have given it again a formula for getting gradient or slope when 2 points are not the same. Then after that, again, give it a formula for getting x3 and y3 for this point. It will give you another point. Let's call it M. then takes this m plus this 2, 4. So it does that until it adds all the points together 5 times. Now, when I did that, I found 2, 1. So then it means my Frobenius mapping had given me this to be 2, 4. But when I added it 5 times, I got it 2, 1. So these two are not equal. They're not equal, and therefore this point is not a member of the group. It's not a member of the group G2. So then I decided to pick another point because, of course, the code will be doing that, going through all the points. So I pick another point that again do the same thing, add it to itself. I decided to check point 1t. Point 1t. So using this endomorphism, it's supposed to be 1 raised to 5, where our p is 5, and the t raised to 5. Now, so what is 1 raised to 5? 1 raised to 5 will just be 5. What about t raised to 5? T raised to 5 will be the same as t raised to 2 times t raised to 2 times t raised to t. The same as. But now, we are working on a field extension of field. Extension field where our embedding degrees 2 and the polynomial I decided to work with, and we've been working with this polynomial from time when we began this. It was this polynomial. This is the polynomial we've been working with. So when I equate this to 0, it means t square is -2. T square is -2. Or when you do it mod 5, it's the same as 3 mod 5. So that's why you see where there's t square, I've written 3. Where there's t square, I've written 3, and this is just t. Now, so this is the same as 1, then 3 times 3 is 4, because we are doing it mod 5. Then times this to be 40. That's why, so using the Frobenius endomorphism, pi of 1t is this. Now, what about 1t added to itself 5 times? When I did this, and of course, we have a code for doing summing. You can also revisit the code and sum. When you sum these 5 times, you get this. Okay, let me just see whether I can open one of these codes, whether you, because we had already written these codes, let me just see where it is. This is where it is, first of all. I can open these codes and to verify where we are summing. We are summing these points. I don't know how I call it, but I can find it. Okay, let me see whether it's this. This one I've seen here. Okay, so it's I think it's this one where we computing want to see the summation of these points. Now our main is okay because we have A as 1 and B as 1, and our P, the point, P is the point. Now that one will change, but I want it added to itself 5 times. Now the point, let's just begin with the point I've been adding here has been, was it 1t? I think it was 1t. 1t. Now, so you see, this is the x-coordinate. This is the x-coordinate. How is it supposed to be? The x-coordinate is supposed to be in the form a plus bt, a plus bt, where a is a constant. And what about the y-coordinate? It's also supposed to be in the form c plus dt, because we are dealing with the polynomials here. Now, so you can see what we have is 1 plus 0t as the x-coordinate, because our a is 1. What about b? B is 0. So that's why you can see I've entered this value as 1, 0. 1, 0 here. 1, 0 at this point. Because the value, it's supposed to be, the x-coordinate is supposed to be in the form a plus bt. A is our constant 1 and b is 0 in this case. What about our y coordinate? Our y coordinate here is also supposed to be in the form c plus bt. So in this case, you can see that the b here, no, yes, or let me call it dt, so that we don't confuse ourselves. So you can see that a d in this case, the point you are referring to is 1t. You can see that d in this case is 1. So that means I'm supposed to write here 1. But you can also see that c in our case is 0. C in our case is 0. So the point is well entered. So I've entered the point as 0, 1. I want to add it to itself 5 times. So my n is 5. My n is 5. So let me just do Kaggle run and see what it gives me. Yeah, so it's saying that if I add it to itself 5 times, the result will be 1 plus 4t. The result will be 1 plus 4t. That is the result we're getting when you add it 5 times. Okay, maybe later on we'll come and see the explanations of this code. But this is just normal summation. This is just normal summation here. You can see this point. Okay, here we're just defining the points on the finite field. The points on how they look like. How they will look like. But what I wanted to mention is the summations. Because we are adding the point to itself. So it begins from here. Summations, it begins from here. It's saying that if one of the points is infinity, and if you are adding it, so if p is the one that is infinity, the result will be q and so on. But now the formula for gradient or the slope are here. The formula for the slope are here. So I think we'll look at this, how it works later. Let's continue with what we were looking at. Now, so we had added 1t to itself several times, and the result I was saying will be 140. And the other number we were adding to itself 5 times, and we got it to 1, was 24. 24. Let's just try and see whether 24 will give us 21. If we add it to itself 5 times, 24. So how does it look like? The point is 24. The point is 24. But we expect it to be in the form Expect this to be in the form A plus BT plus BT, and then the XY coordinate, expect to be in the form C plus DT. So you can see that our constant A is 2 in this case, and our constant B is 0. So then I would write it as, I will write the X coordinate. This is the X coordinate. This is the X coordinate. The X coordinate, the constant part is 2, and BT, B is 0. B is 0. So what about the Y value? You can see the Y value here is 4. So I'm relating it with this C plus DT. So it means C in this case is 4. C in this case is 4. In this case, C is 4. What about D? D is 0. D is 0 in this case. So then let's run and see whether it will give us 2, 4. No, 2, 1. We had found the result is 2, 1. Go run. Yes, it's saying that this point added to itself 5 times, the result will be 2, 1. So what this means, that part of this, when you're writing the code for getting G2, and we are talking about G2 and G1. So when you're writing the code for G2, part of this will be that code, part of this. You only need to modify this. Because this one is giving you, now you ask it now to do for every point, so that you're not giving it a point manually. Because for this case, we are giving it this point manually. We're giving it this point manually. But now you ask it to go through all the points of the finite field and then sum each one of them 5 times, and then see the ones that obeys the Frobenius endomorphism becomes the members of the G2, or group 2. Now, so we've just found out that point 1T will be a member of that group. Point 1T will be a member of that group because it has obeyed that endomorphism, Frobenius endomorphism. It has obeyed it. So this becomes a member of this group. So then we are doing it for all the members of finite field, all the points on the elliptic curve in the extended finite field, and checking. So when you do that, you expect to get, so I also decided to check this other point, because this was another point, on the elliptic curve. Now, so I decided to do the Frobenius endomorphism here. And what does it say? It says it will be 1 raised to 5, then 4t raised to 5. So 1t, now 1 raised to 5 will just be 1. What about 4t raised to 5? 4 raised to 5 will be 1025, then it raised to 5. No, 1024. 1024 t raised to 5. Now this one, you can always, 1024, you can always reduce it. You can always reduce it mod 5. When you reduce it mod 5, what do you get here? You're getting 1, and reduce this mod 5, it will be 4. Then t raised to 5. 4, and then t raised to 5. T raised to 5, we just found it above. We've just done it above there. T raised to 5 was giving us 4t. So this will be 1, then 4, 40. So 4 times 4 will be 16, mod 5, that is 1. 1t. So that's why I come up with that. Now, so the Frobenius endomorphism gives us that it will map a 140 to 1t. Now let's now add it to itself. Let's add 140 to itself 5 times. When you add it 5 times, again, you can use the code you just used before. When you add it 5 times, gives you 1t. Gives you 1t. So you can see that it's evident that this equals to 140. It equals. So that then means that this point again is a member of our group G2. The other member, of course, will be, so we've already obtained 2 members. So the other member will be the identity element, because we expect that the identity element will always be mapped to the identity element. And of course, we also expect that if you add the identity element 5 times, the result will be the identity element. So again, these 2 are equal. So we then have already obtained our 3 points we sought to find. Because from the start, we knew we're going to get 3 points. So we now have our 3 points that form our G2. So we have our G2. This is our G2. So we obtained above, and we also have our group G2. So now when we'll be doing the pairing itself, the Weyl pairing, we'll be choosing 1 point from this group and another point from G1. And we want to see, we'll be using some algorithm to see where that product will then be mapped to. Where that product will then be mapped to. That is when you'll be looking at that point, we'll be looking at Weyl pairing and the other types of pairing. But today we're just seeking to find out how do we find these 2 groups that we'll be working with, G1 and G2. Now, again, I'll repeat, do another example so that we are very familiar with how to get G1 and G2. I pick another elliptic curve, and this one is y square is x cubed plus 8x, and then plus 8. Plus 8. This elliptic curve, earlier on, we had found that it has 20 points. This is the order of this group. The prime divisors, the prime factors of 20 are 2 and 5. So now we find the 5 torsion group. I've not talked of 2. Our G1, where we have several divisors, where we have several factors, like in this case, our G1 would be one of the highest. You pick the highest R. Pick the highest R. Of course, the highest R will give you the highest embedding degree. And that's what you're looking for. You're looking for one that has the highest embedding degree for security reasons. So then we choose 5. So that's why you can see I decided to find the 5 torsion group. 5 torsion group. So the 5 torsion group gives me my G1. What about G2? Okay, this one is supposed to be, I didn't type properly. This is supposed to be identity. Supposed to be identity element here, just like this. The first entry here. Now, so of course, this will also have 5 elements. 1, 2, 3, 4, plus the identity 5 is 1, 2, 3, 4, 5. Each of these group have the same order 5. Our R, and I've said our R will then pick the highest divisor of the order. Where you have several divisors, they will pick the highest. But in a case like the one we looked at earlier, the example that had 9 as the order, the only divisor was 3. So in that case, there's no problem. Now, so these things you can do them manually because what we are doing here are smaller. These are smaller elements to deal with, smaller, the smaller P, order, the smaller order. So, but when you're looking at very huge order, it might be easy for us to do it manually. Now, so again, I just used the code and then wrote those results. So I didn't, but of course, you need to know what these ones mean. You need to know every point here, every point that is here is one database that 5P should give you the identity element. So these are all these points, multiply them 5 times, get the identity. Let's just again try. Let's just verify. Let's verify 8, 8. I can see 8, 8 here. It's easy to recall that. Let's just use our code. And we want to add it 5 times, 8, 8. And we want to see whether it gives us identity elements. Now, I just changed the parameters. In this case, our A, let me see. Our A is supposed to be what? Our A was 8. What about our B? Our B was also 8. What about M? M was 13. Our R is 5. Okay, let me just check whether this code was just for the previous example or whether it can perform other examples. That's what I'm trying to check. Because you see, in most cases, when we're using those polynomials, for the previous example, the polynomial was t raised to 2 plus 2. But in this example, the polynomial is t raised to 4. The polynomial is t raised to 4. But let me just check here. Have I entered the point? Getting the arc torsion. I wanted the one for getting summation. Okay, let me try this. Yeah, I think it's this one. 8, 8, 5, 8, Yes. So when you add 8, 8 says the sum is a point at infinity. It says the sum of this, if you add that point to itself 5 times, the sum will be point at infinity. So that's what I was saying. That's what I was saying, that each of the points in the G1, each of the points in the G1, adding it to itself 5 times is supposed to give you point at infinity as the sum. What about this? Again, remember what is happening here. What is happening there is that we are using the Frobenius endomorphism, and it says you check whether phi of a point will be the same as, in this case, 5 times. Check whether pi, this pi will map this. Where pi maps to this, that result, whether the result is the same as this. And what is this mapping? This mapping is saying it maps xy to x raised to 5, then y raised to 5. That's where it maps. So you would then be checking this, you'll be checking this result, if these are equal. Now, so now I want to take you to the codes that are doing this without doing it manually. That's what I want us to look at. Okay, give me again just 1 minute, just 1 minute.